Greetings, Mick McQuaid here, welcoming you to day 12, the end of week 3 of iste780, Data-Driven Knowledge Discovery. And today we're going to do 3 labs. Is that right? 3 labs? I think it's 3 labs. Anyway, in this particular video, we're just going to do the first lab, which covers subset selection. And so that's got best subset selection forward and backward, and choosing among the models using validation and cross-validation. Okay, let's begin. Now, to save time today, I've got a bit of a time crunch here for reasons I won't go into. I'm going to use the version that I've already typed in here of the commands. So I'm just going to run through them rather than actually type them in. So ordinarily I'll type them in. So I've already opened R here. I've already opened my text editor. And we're using the ISLR library plus another library that you're going to probably have to download. Actually, I can't remember now if it's a default library or not. Anyway, we're going to be using the hitters file, or the hitters data set. And this is about baseball hitters. I'm going to set my width to 140 because of reasons that will become apparent later. Okay, now hitters only has 322 records, but it's actually got a bunch of records with NAs for salary, and salary is the response variable. So we want to figure out what they're paid. And by the way, I've had previous students do projects on baseball data. I don't think it was this particular baseball data, but they've discovered some interesting issues in pay versus performance that contradict some stereotypes that this was a really interesting project. They found newspaper articles with sports page articles with stereotypes about highly paid baseball players, and then they refuted them. It's kind of like 538. If you ever look at the website 538.com, which does a lot of baseball stuff. It was founded by Nate Silver, who was a big baseball expert before he got into politics. And basically what my students did was the same type of thing that they do on 538. They used data to refute stereotypes. Really fascinating stuff. Okay, so now we're going to get rid of these 59 NAs for salary, because we're going to use salary as the response variable. I said that already, didn't I? So now we have 263 rows in this data set, and we have no NAs. Okay, now we're going to use this library LEAPS. And I have to admit, I don't remember whether I downloaded this library or not. There is at least some library that we'll be using today. I think actually multiple libraries that you're going to have to download. And remember, when you do download, make sure that you install dependencies. Otherwise, you're going to be downloading all day. Okay, so what we're going to do is do a full regression, full model of all the items. So if you take a look back up here, you'll see that we have 20 columns. So one is salary, so the other 19 are predictors. So we have as many as 19 possible predictors in this. And if we take a look at the, and here's why I widened to 140 columns. If we widen to 140 columns, we see this is the order. This tells us the order in which the predictor variables were brought into the model. So we have, and this is, by the way, this is a default. It by default goes to 8 eight models. We're gonna, in a second here, we'll do more. But we went up to 8 models here. The first model just has CRBI. Something runs batted in. What is it? What does C mean? I'm not sure. The second one has hits and CRBI. What is CRBI? Because here's the RBI. Okay, well, in any event, then the next model has 3 hits, CRBI, and putouts. And then so on, and until we get the 8th one has the most variables in it. Okay, now we're going to do the full 19. NV max says number of variables max is 19, so we're going to, instead of going up to 8, we're going to go up to one with 19 in it. And let's do a summary of that one. And there's a bunch of stuff in that. The summary of that has all these columns. And you know from yesterday that we're using, R squared, RSS, and R squared and RSS. And then we have these methods for selection, the adjusted R squared, CP, Bayesian information criterion, and we don't have the Akaki information criterion here. All right, so anyway, let's take a look at the R squared. And this isn't going to look that great. Oops, I know the last time I did this, I did digits 3, so it would be easier to read. And what we see is that we go from a low of 32%. So remember, R squared is the proportion explained, and the lowest explained here looks like it's about 32%, and the highest explained looks like it's around 54. Quite a lot of these are at 54%. Okay, so let's do some plots now. We're going to take some plots of not only the I hope this is going to be good. Let me try it like this. We're going to take some plots of RSS. So remember, we want to minimize RSS. Adjusted R squared, we want to maximize adjusted R squared. And notice that although R squared increases monotonically, what's happened here is that as we added more variables, adjusted R squared increased and then decreased a little bit. And then we're going to put some dots on these. So what is the largest value of R squared? It's the one with 11 variables. So this is just what is the max of these, and we get the answer 11. So points is like a plotting command, but it just plots on an existing plot, plots points on an existing plot. So we just said we wanted to plot the position of the 11th item in our summary there. You know what? I just realized. Let me go back to line 19 here. Here's something that might elude you. If you look on my copy here, it's obvious, or line 18 for that matter, it's obvious that this says type is equal to L. If you do it straight out of the book, you may make the mistake, as I did in typing. I typed a 1 instead of an L there, and of course that did not work. So I meant to mention that. I'm really speeding through this, I guess. Okay, so now we're going to do Mel Ocp Criterion, and we're going to find which is the minimum there, and we're going to plot that point. So notice that in the adjusted R squared, the maximum was achieved with 11 variables. The minimum CP, though, was achieved with 10 variables. So this is working differently. And then RSS just keeps going down, so that there's no point in trying to plot a minimum here. Okay, and then we're going to do the same thing for the Bayesian information criterion. And look, here's another difference. This one is only 6 variables. So let's plot that one. And we're going to plot that position number 6 there. And what am I plotting here? I've completely forgotten now where I am. Scale R squared. Oh, okay, so this is the built-in plotting function. So I should point out that, this is an object-oriented language, and so the objects... Now that's funny. Let me adjust this. Why did that not work? There we go. Okay, so it's really, really tiny. So this is a plot method in the reg subsets object, and this is telling us like what's being brought in. which variables. See, here are the variables, and this is telling us which variables are being brought in, and also it's shaded slightly for the value of r squared. And we're going to do the same thing with adjusted r squared, and same thing with CP, and same thing with Bayesian. And so you really have to enlarge these beyond what I can do on this display to see them and to see the differences in the results here. But this is just basically telling you graphically the same stuff that we got back here when we, except that it's giving you an x-axis before when we did. Let's go back up here and do this one more time. What was one that we did here? I think yeah. So anyway, here's the list in non-graphical form, just in terminal character-based form, the list of the variables which appear on this chart. And when we brought them in, the difference with this chart is that it also shows the value of the variable along the y-axis. So we see, so for adjusted r squared, we want it to be as large as possible. R squared, we want it to be as large as possible. And drat, I can't, how can I get, I can't really get the other two on this display. Oh, I guess I could move the whole display down, but I don't want to do that. So just do it yourself. Do all of these plots yourself and look them over. So obviously for Bayesian information criterion, we want to maximize it, but for CP, we want to minimize it. All right, I'm just going to move this over here and try to remember where I was. Let's see, we did these plots right here, and what are we finding out here? Oh, okay, so this is the best model according to Bayesian information criterion. These are the 6 points. So whichever one we do, so I could substitute 10 or 11 here if I wanted to take the best one from adjusted r squared or from CP, and these would be the coefficients of these would be the beta values, the coefficients of the x's. Okay, now we move on to forward and backward. So that was best subset selection, and it's tough even with 19 predictors, but impossible if we have 40 or so predictors. So what we're going to be much more likely to do is forward or backward. So let's do forward here, and let's look at a summary of forward. So here we're doing forward, and we see this roughly the same order, but not quite. It's not quite exactly the same order. And if we do backward, we also get a different order, and I can't remember now. I looked this over. Look it over closely, and you'll see where it starts to diverge. Oh, and here's an example. So let's look at these three. Okay, so you can see here that the best has, or the full, I should say, the one that we used for best, has at bat here, and oh, it has walk also. So they all have walk. These have at bat. C at bat. I wonder what does C mean. See, I'm not a. So there's a slight difference. A home run only appears here. CRBI. Gee, I thought CRBI would have appeared in all of them, but it doesn't. It appears in forward. Am I missing it in the other ones? No. Interesting. So it appears in forward, but not in the other ones. Okay, so anyway, you can see that these give slightly different results, slightly different sets of coefficients. Now let's do validation and cross-validation. So first I'm going to set a seed so that we get the same results as the textbook. And I'm going to create a training set and a test set. So the training set from hitters is a random sample from hitters, and it's a random sample where I'm using the number of rows in hitters to determine the random sample. And the test data set is just whatever's not in the training data set. Okay, and then I'm going to I'm going to fit the model using the training data set, and then I'm going to create a test matrix using the test data set. And I'm going to take the validation errors as first. I'm just going to repeat NAs 19 times, and then I'm going to create a little function here that's going to go, or a loop here that's going to create a new validation errors list based on removing these NAs and replacing them with the coefficients from making the prediction each time. And so there are the validation errors. And so then the question is, where do we get the minimum? And it's at 10. So it agrees with, I guess, the adjusted R squared. So the coefficients for the fit for the 10th time, when we add it, we added a total of 10 variables to the model, wins in the validation method. So now let's create another function, and this function actually I think we're not going to use right away. We're going to use it for cross-validation. Okay, and then I'm going to do this again. And I get a different result here. So I'm going to say k equals 10. So this is going to be k-fold cross-validation with k equals 10. And folds is going to be a sample of 1 to k, so a sample of 1 to 10 from hitters, the number of rows, I should say, of hitters, which I think is 263. And we're sampling with replacement. So there may be more than one copy of a particular value in here. And now I'm going to create the cross-validation error matrix. And I'm going to do this little loop. Let me just put the whole loop on the screen. This is a little double loop. And in the inside loop, we're going to use the function that we created up here. So this function is a method for reg subsets. So when we call this function down here, all we have to do is say predict and call this function on an object of the reg subsets type, and then R will know what to do with it. And so there are the mean cross-validation errors, and they seem to range from about a low of about, 12,000 to 16,000. And now let's take a look at a plot of them. So let's start our plotting. So here's a plot of the errors, and you can see we go down. So 10 and 11 look, well, 11 actually looks the best. And here are the coefficients for 11. I'm even not wide enough there. Okay. So anyway, that's the end of this first lab. And as you can see from this, the next video is going to go on to lab 2, ridge regression and the lasso. But that's it for subset selection. Thanks for your attention, and I'll talk to you again hopefully today.